Greetings and welcome to this tutorial. In this video, we are going to deal with the third law of thermodynamics. Just like the first and second law of thermodynamics, the third law also forms a very important part in thermodynamic studies. And it's really important while we are dealing with thermodynamics problems. So the third law is related to entropy. So first, let's understand the statement of the third law. The absolute entropy is zero for a perfectly crystalline substance at absolute zero of temperatures. All right, this is the third law. This is the statement for third law. Now let's understand absolute entropy. What do we mean by absolute entropy? All right. So before that, let's actually consider the calculation of a simple quantity. Let's say enthalpy. So we are going to calculate enthalpy at any temperature, let's say 500 Kelvin, and its Cp is known. The Cp of this particular substance is known, right? Now, the question is that how do we calculate enthalpy? So enthalpy can be simply written according to the equation dH is equal to Cp dt. Hence, we'll get delta H would be integral Cp dt from one particular temperature to another particular temperature. And on the basis that we can write H2 minus H1 is equal to integral T1 to T2 Cp dt, right? Now we know Cp, that's not a problem. And we also know T2, that is 500 Kelvin. We need to calculate H2. So now what should be done with H1 and T1? How do we know what are H1 and T1? So in order to solve this particular problem, what we actually do is we define something called a reference state. We define something called a reference state. So generally, for example, for case of water, we take reference state as 273 Kelvin. And at this reference temperature, the enthalpy is taken to be zero. All right, that's how we deal with it. So then we'll put this as 0 and we'll put this equal to 0. And then we can simply calculate H2 is equal to integral 0 to T2 Cp dt. And since Cp is known, T2 is 500. So we'll get 500 Cp as the result, right? But over here, we had to define the reference state. We needed a reference state. And this reference state would vary for different substances. For example, over here, we took water. So therefore, we defined the reference state at 273 Kelvin and took the enthalpy as 0. Let's say I'll take some other substance, let's say carbon dioxide or nitrogen or something else. So in that case, the reference state would vary. We do not have a fixed reference state for which we can actually say that the enthalpy at that particular temperature is always going to be 0. So that's one problem that we deal with calculations of quantities like enthalpy or internal energy or something like that. But the third law solves this problem for the case of entropy. For the case of entropy, this particular law, the third law, is very helpful in solving such problems. So it clearly states that the absolute entropy is 0 for absolute 0 of temperatures. So absolute 0 of temperatures means 0 Kelvin. And absolute entropy means entropy at a particular temperature. Like over here, this is absolute enthalpy at 273 Kelvin, right? Similarly, this is going to be absolute entropy at, let's say, 0 Kelvin. So the absolute entropy at T equals to 0 Kelvin is going to be 0 joule per mole Kelvin, right? It's going to be 0. Absolute entropy is 0. Now, since absolute entropy is 0, and that does not vary with the type of substance, right? It does not vary. Like, for example, if we take carbon dioxide, that's also going to be 0. If we take water, for that also it's going to be 0. If we take nitrogen, for that also it's going to be 0. So it's uniform. So this particular problem, which we actually faced with which we actually faced with enthalpy is solved by the third law for entropy related calculations. So now we can simply say that for calculation of absolute entropy at any given temperature, we have a fixed reference state, irrespective of the substance, irrespective of what we are dealing with. We can always take absolute entropy at 0 Kelvin equal to 0. So if we go on to calculate entropy, just like we calculated enthalpy, we simply calculate entropy. So let's say we go on and calculate entropy. So in that case, we are going to have ds is equal to integral dqr, integral ds is going to be equal to integral dqr by t. So this is going to be from S1 to S2, and this is going to be from T1 to T2. Now, this can be the reference state, and by third law, we can take this as 0 and we can take this as 0. So we can simply get S2 minus 0 is equal to integral dqr by t from 0 to T2. So the problem is solved. The problem is solved. We do not need any other data. We simply need the temperature and we'll get that. Right. So this particular problem, which we actually have while we're dealing with enthalpy or internal energy, this is not a problem while we're dealing with entropy because of the third law. So the third law is basically giving a general reference state for entropy calculations for all substances, irrespective of their type. All right. There are just two conditions to be followed. First, that the system must be perfect crystalline substance. It should be a perfect crystalline substance. There are substances which cannot be crystalline, which cannot come in crystalline form, even if you reduce their temperature to an absolute 0. So for those cases, for those substances, this law is not going to be valid. Okay, this law would be valid only for substances which are in a perfectly crystalline state. Okay, perfectly crystalline state, and they are at absolute 0 of temperatures. All right, so in that case, the absolute entropy is going to be 0. Okay, so based on this, let's solve a very simple problem. It is known that the molar heat capacity of a substance at low temperatures can be approximated by the relation Cp equals to At cube, where A is a constant. Determine the molar entropy of a metal at 10 Kelvin. Now see, they have just mentioned that it's a metal. We do not know what it is. We do not know what is its kind. We don't know anything. So if we go on to calculate the entropy, if we go on to calculate the enthalpy, so we'll need a reference state. But since we do not know what kind of a substance is this, what metal is this, we won't be able to easily define the reference state, right? But that problem is solved for the case of entropy calculations, because we know by the third law that at absolute 0 Kelvin, the entropy is going to be 0. So we have a universal reference state, that is T equals to 0, which gives S equals to 0. So because of third law, this problem is solved for the case of entropy. So this is a very simple problem. We simply need to calculate entropy. So entropy is equal to Cp dt by T. And we are going to integrate this from over here. We are going to integrate from 0 to S. S is the absolute entropy. And over here, we are going to integrate it from 0, that is absolute 0, to 10, which is the given temperature. Okay. And also they have given Cp equals to At cube. So over here, we'll use this and we'll, I'm so sorry. Cp equals to At cube. So we'll simply put Cp is equal to At cube over here. Dt by T. That's this. And then we'll have this as At cube by 3 between 0 and 10 Kelvin. So that's going to be A into 10 cube by 3 minus 0. So that is going to be 1000 by 3a. Okay. Now, one thing that they have given, that at t equals to 10, Cp is equal to 0.45. So from here, we can get A is equal to Cp by T cube, which is 0.45 by 10 cube. So we'll put that value over here. So we'll get 10 to the power 3 into 0.45 upon 3, and over here upon 10 to the power 3. So that's going to be this. And this is going to be 0.15 joule per mole Kelvin. So as you can see, we have calculated the absolute entropy of the metal at 10 Kelvin without any previous data given to us about the reference state. So this type of a problem can be easily solved for the case of entropy. While if we want to calculate the internal energy or enthalpy, absolute internal energy or absolute enthalpy, then we would not be able to make the calculations. All right. So the third law has simplified entropy related calculations.